I hope it works. I hope this thing's on. But we get to hear you. You want to say something? No?
No.
Anyone?
Hello.
Okay, and then you'll hear that.
Hey.
Millions on YouTube. Okay, that's enough. All right. It was just a little too far. All right. Here we go. Polynomials today. We're going to do the polynomial dance. But we're going to go over the basics first. What you need to know. You already know this, though. You've already used this notation. Like I said, this book is redundant a lot of times. Not sure why, but it's okay. You know, if you didn't pick up something before, now you know. So the first thing I put is x squareds. And by the way, if you want a whole encompassing, what is this first page all about? I kind of put four situations here, and then from that we make a generalization. So I'm going to zoom back. I'm sorry, going the wrong way. A little discombobulated. Okay, so first thing, x squared is a picture of a what? Parabola. But one thing you got to note here is, you know, this was partially like your Algebra 2 notation last year, but if you had me, and I think the other teacher did that too, we turned it into limit notation because it does mean the same thing. So as x approaches infinity, what this means is, you know, I'm going to put this down and do the fingers on the board, but, you know, what I did with my students last year was x finger, y finger. So here's the x finger, here's the y finger. That's where the y is. What happens as the x's increase? What do the y's do? That's what this notation is over here. That's what limit notation means. We're going to hear that cough. That's awesome. I think it's tell mom, dad, parent, or guardian, hey, that was me coughing. All right. Anyway, so parabola, as I plug in infinity for x, I get infinity for y. Another way, a very simple way of doing this is, what's a... Oh, brother. What do I do?
X.
Hold on. Oh my gosh. See what it takes just to get me all discombobulated? All right. Okay, I forgot what I was saying before that happened. What's 100 squared? What's the answer to that? A big number. It's actually I got to think about it. 10,000? Right. So as you plug in big x's, the y's get big. What's a negative 100 squared? What's a negative 100 squared? Positive 10. So that's what end behavior actually is too. You can actually physically plug it in the situation. You right over here? Twirling? Okay. All right, so what we do is with limit notation to describe that, there's those two answers. All right, actually four for the quadratic. And then when you plug in a cubic, and actually I plugged it in for you. You know this from last year. This is what the polynomial dance is. This is what a just x cubed looks like in a negative x cubed. So I think we can answer these questions now simply. But I'm going to get the calculator. So individuals answer those. I think this is, you know, I think we know this. This is going to be fine. All right, so let's move on faster. Let's go to x to the fourth. Now, this one is just x to the fourth and negative x to the fourth. What does it look like? It looks like a parabola because I don't have anything else in there, like an x cubed, an x squared, and that you're going to have that. So what this looks like is a parabola with kind of like a wider approach to that 0, 0 vertex. All right, so it's very simple, but the end behaviors are exactly so. I don't even want to bother anyone with this. Everyone should be able to fill these out and probably not even put these on their notes. Okay, as x approaches infinity, what does y approach, everybody? Infinity. What's this next one down here? Infinity. What's this one over here for the upside down one? Okay, so just know when they ask you to do limit notation, this is what we're doing. So what would an x to the 6th, an x to the 8th, an x to the 10th look like? What would it look like, and behavior-wise? Just like that. I have a student number 7 doing the dance. All right, now x to the 5th, what does that look like? What does x to the 5th look like? An x to the 3rd, and also an x to the 7th. What else? Blah, 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 9th. All right. And actually what happens, you're going to get more stuff after the x to the 5th smaller degree that gets some loops going on in there, little roller coaster things. But the end behavior is taken care of. And I put this as like coordinates. If I were allowed to plug in infinity for x, I would get infinity for y. So that in theory is a coordinate. That is why this is the answer for that limit. If I plugged in a negative, what's a negative to the 5th power? This is why the end behavior is what it is. What's a negative to the 5th power? A negative. So if I plugged in negative infinity for x, I would actually get negative infinity for y. It's another way of looking at it. Okay, sorry for that sloppy negative infinity. Everyone standing up in class. Here we go. Show me the polynomial dance, what this would look like. Ready, set, go. Boom. Use your arms. Okay. Oh, this is so great. There's like so many different answers. Okay, let me see. That's a negative 3x squared. So what does it look like? Good. Nice. Okay. Next. Boom. You have 5 seconds. 4, 3 to get your final answer to. I love how everyone's looking around. 2, 1. Good. You had some changes in there. That's a 2x to the third. So kind of easy start. Next one. 5 seconds. 4, 3. I shouldn't have it highlighted. 2, 1, 0. Everyone's good. Last one. 5, 4, 3, 2, 1. Oh. 0. Okay, have a seat. Okay, so we had everyone stand up, and then this is the actual pictures. Boom, boom, boom. Oh, now we got some roller coasters, and boom. And then take a look at the third one. What do these things at the bottom mean? What are these negative 10 to 10, negative 50 to 50? What is that? Because your book does this. What is that? The window dimensions would probably work as well. So whenever you see a picture and these little things are down at the bottom, this is the first one's the X window, the second one's the Y window on the calculator. And look at the fourth one. And I'm going to over-explain it because that's what I do illegally. I teach students. So why does it end like this? Well, that's a good question. Thank you, Mr. Samuelis. It's because when I plug in like 100, this takes over. And even though 100 cubed is a lot, and 100 squared, the 100 to the fourth dominates the situation. It actually makes this less significant. And all I have to ask you is, what's 2 times 100 to the fourth? What kind of number is that? It's a very large what? Positive. And then what happens when I plug in a negative 100? What's a negative 100 to the fourth? A very large positive. And even though a negative 100 to the third is a negative large number, it's not big enough to affect the negative 100 to the fourth. So that is why when I plug in big negatives, the x to the fourth dominates and turns positive for the y value as far as the coordinates that I plug in. So that's really the reason, as opposed to just, okay, this is what Mr. Samuels said, he makes me do silly dances. Well, that's the reason, and that's why what happens happens. I did this last year. I'm almost positive we're not even going to fill in these end behaviors because we know them so well. And then actually the book does a great job of explaining the same thing that I just did. Whenever you have an odd degree, look at the leading coefficients. The leading coefficient is positive, you'll have end behavior like the first one. If it's negative, it's like the second one. That's what we just did. And then if you have an even degree, I don't care if it's an x to the 12th is the top dog. If it's a positive x to the 12th, at least the ends will be the same. Everything in the middle will be different, though. You get more loop-de-de-loops, if you will. Look at that third one. This one's a real special one. All right, 1, 2, 3. Hey, I should have said that. Look at how many directions there are. How many directions are there? How many increasing and decreasing parts are there? 4 total. Does that mean an x to the fourth always has 4 directions? Yes or no? No, because you forgot that the first one we did right there was an x to the fourth. How many directions does that have? 2. So what you would say about this, and I said this in second hour, if I didn't give you this equation, but I gave you the picture, and I asked you what's the degree of that, you'd have to say at least, yes, at least what? No, this one. At least what? It has to be at least 4. It can't be an x squared. It could be an x to the 6th. It could be an x to the 12th. All right? But we know at least it has to be an x to the 4th because of the terms. What will we say about this one? Well, I know you see the answer. Could that possibly be an x to the 3rd? No. You know why? There's a little what in there? A little bump, a little wrinkle. All right? Little wiggle in there, if you will. That little wiggle just added 2 more degrees. That wiggle in there, that means that cannot be an x to the 3rd. All right? So make sure you understand that as well as far as minimums. All right, just did the polynomial dance on this whole page of notes. All right, now I'm going to actually just explain it. I forgot to erase that. So literally off of what I just covered before on the video, before we did the polynomial dance, is which one of these four could this possibly be? Only this one. Why? Because there's a little what here? Little bump, little wrinkle. So this could not be an x to the third anymore because that actually is a little bit more character created by 2 more degrees in this. So this would minimum be an x to the fifth. Can't be an x to the third. What's this? That's a negative x to the third or more. And then what's this? A negative, right? X to the fifth or more, but it couldn't be an x to the third. All right, and then the next thing, I'll just have you look at this stuff so you understand. We'll zoom in. All right, and this is something you're going to need to understand for your quiz Thursday. No graphing calculator. All right, you're going to need to understand that this is in factored form. Actually, I already had this on there. If you FOIL it out, it actually literally would be 1x cubed plus blah, a whole bunch of other stuff. What are the x-intercepts of this picture, though? That's what you're going to need to know. What are the x-intercepts? 1, 0. What else? Negative 2, 0. What else? And then you're going to have to actually come up with this drawing without a graphing calculator. So you're going to have to say, okay, negative 1. Wait, 1. Never was good at math. Negative 2, negative 3. And then, oh, it's supposed to look like this. So how would the graph fit those x-intercepts? Like this. Bloop, bloop. And then we're going to do more of that. And then, of course, a whole bunch of limit notations on those questions if they ask you. Just write it down and get used to it. Next, I should have you plug this in, but I won't. I'll have you plug in one that's a little bit more challenging later. This is going to be your job as a student. You're supposed to know that this is, and you already did this when you stood up. Well, I accidentally had it on there when we did it. It wasn't very exciting. This is the end behavior of this. Then you type it on your calculator. And then you see this picture. What? Well, you're supposed to know that. All right, well, your brain says, uh-oh. Okay, good. Your brain says that this must be that one of those loops, and then this connects here, and then this connects there. So you're going to need to what to see the whole picture? Actually, who do we really need to affect only? The X's or the Y's? Y's. I'm going to warn you. I will get sadistic, mean, jerk. I will put what's this called? A polynomial. Thank you. You're welcome. A polynomial that when you hit zoom standard, you'll see nothing. Nothing at all. You got to know as a student, and then you come over and my calculator doesn't work. I'm going to say, sit down. All right, you need to know what you're doing. You need to zoom out, and it's a trial. Say it, trial and. But this one's not. That's a lie. This one, you actually see enough to make a decision to change the Y mins and maxes. So I can see the loops because I actually see enough behavior to understand it. Does that all make sense? Take that lack of response as a yes. Doing this without a calculator, we already did that when you did the end behavior. This is the top dog right here. Right? So what happens when I plug in 100? The negative 100 to the fourth takes over. All right? Actually, it's 100 raised to the fourth, then a negative put on it. So the end behavior will be this. So these two limits would be that and that. Takes no graphing calculator, no long analysis. It's just the polynomial dance. Got it? Okay, this seems to come out of nowhere, but it doesn't. Actually, this would help you graph this. Okay, when it asks you to find the zeros algebraically, that means you need to factor. Let's go ahead and do that real quick. I'm picking 2 students just because it's fun. Okay, now you're on. What are the x-intercepts now that you've unfoiled? Because that's all we did was unfoil. And these are just checks for the middle term. So what are the x-intercepts?
Negative 2.
Let's say negative 2, 0. And then what else?
2/3.
And then you set the other one equal to 0 and solve. So we're doing the zero product property. Okay, and then who's next? Let's get another student. Shipao, student number 23. You're on. Yeah. Were you 23 last year too? You don't remember? Okay, all right. Which way does this, what is this a picture of, by the way, 3x squared? What's that a picture of? Parabola. Which way is it facing? Up. What are the x-intercepts? That's already up there. Fumble. All right, and then what do you draw? I don't know what else to say. What do you draw? Parabola. This is how it fits. So you can make a sketch on this. How could I, volunteer-wise, how could I find the vertex of this so I could get a little bit more shape out of this? Two ways. Complete. Or negative b over 2a and then plug it in. So you could get more out of this. That would be enough to get that picture. All right, good stuff. More than an x. You made your life miserable. Huh? Sorry for yelling. I don't do that often. All right? Very nice to the students. What do you get left over?
X squared minus x.
Okay, did you factor that yet? This says just find the zeros. The zeros are 2, -1, and 0. You said 0, right? Because I wasn't really listening. I'm sorry. I have a hard time doing two things at once. And then you did the polynomial dance. Do it again. So the only way that this fits is this. So if I asked you to make a sketch out of that, it's done. It fits the 5x to the third mold. All right, and it actually has 3 x-intercepts. Does a x to the third always have to have 3 x-intercepts? Yes or no? No. One thing that you should write down is this. Because these are, I kind of call them synonyms, although that might not be the appropriate word. Let's just say all of these terms are related 100%. One creates another, so to speak. So what you found in that last one is the zeros of the function. So what that is the number for x up there that makes the equation 0. That's why it's called a 0, which is also the solution for the equation, or root. Can everyone say root? Root. It's actually root, isn't it? I don't know. All right, but then what happens after that is zeros turn into x-intercepts for the graph. So zeros turn into x-intercepts when you look at the picture, because that's where y is 0. It's all related. And then, of course, zero solutions, roots, x-intercepts come from factors in a polynomial. And we know all that, and I have a little thing off to the side that kind of shows that. We all stood up again, some begrudgingly. Look like they want to kill me when they're doing the polynomial dance, but that's okay. All right, so this is what you need to know on this, and you may have already known this from last year, but if you want to be a note taker, fine. A couple of things at the end you're going to definitely have to at least take note of it. Factors, like I left that box up there for you to write down, turn into zeros, which turn into x-intercepts. Now, before we did the polynomial dance. We know if we multiplied this out, this would be negative 2x cubed plus a whole bunch of stuff that is smaller in degree. So 100 cubed is a large number. But what happens when you multiply that by negative 2? It becomes a negative large number, or actually more appropriately, a very small number. You know, negative is small. So that's why the end behavior is this. And then what's a negative cubed? That's my question. What's a negative cubed? A negative, but what's a negative times negative 2? Positive. That's why on this side, when I plug in big negative x's, the y turns very large positive. That's what's happening with this end behavior, what's going on, and you need to understand that. So then what do you need to do and understand? X-intercepts come from zeros, from the factors. You could plug those x-intercepts on a grid, and then you could graph it by fitting that behavior that's supposed to happen. That's what you're going to do. But this one's special. What's special about it? One of the factors is squared. So we all did the polynomial dance, and we said this is a 1x to the 4th, so I can expect this behavior in some way, shape, or form. But something special happens about this. I just asked the question, does an x to the 3rd have 3 x-intercepts? Not necessarily. Does an x to the 4th have 4 x-intercepts? Not necessarily. See, what happens special, and this is what you might need to write down because I don't know how else I can approach it, is when you get a multiplicity 2. By the way, everyone say that. Multiplicity 2, 0. That just means a 0 that came from a squared factor. That means x equals 2 twice. Well, it doesn't create 2 x-intercepts. It only creates 1. So what happens with the picture? And actually, I could explain it with a parabola. You know, if you just had a parabola y equals x minus 2 squared like this, you know that this is just a parabola shifted to the right twice, and it looks like this. What's the graph doing to the x-axis? It is just what? Touching but not going through to the other side. That's actually called tangent. That sounds like a trig word. Tangent to the x-axis at that double zero. So you need to know that. You put these normal zeros down, -1. You put 2 down, but then you say to yourself, wait a minute, that's a multiplicity 2. That should bounce and be tangent to the x-axis at that position. And then this is a regular 0. So you put the end behavior together with the x-intercepts and also the multiplicities, and you get it figured out. Student number 1, 4th hour, answered the question correctly. What happens with the multiplicity 3 scenario? I'm just going to shove it in your face and just show you what it is. But you know, I could explain it. It's related to what happens with y equals, let's say like x minus 1 cubed. You know, that's still a cube root graph that looks like that. Remember the book of functions? Remember that? And then we got that little flatness in the middle. Remember that? No one's saying a word. It's like I'm alone in here. I'm actually taping myself in the classroom, talking to myself. Not really. All right, and then this moves right 1. That's all that happens. But again, what does it do as it crosses that x-axis? It flattens out. So you're going to need to know, and you're going to need to show, that just rhymed, that, okay, we got a multiplicity 2, 0, but you're going to need to show the character of a multiplicity 3, 0. As a fact or mact, I showed the graphing calculator. Look at that. So when multiplied out, this would be a 1x to the 6, blah. The end behavior should look like that. Here are my x-intercepts. One's a multiplicity 2, one's a multiplicity 3. And that's what you have to state. Mult 2, mult 3. I could really go for a mult right now. Anyway, flattens, bounces, no character, straight through. Knowledge. Okay, so did the polynomial dance again on these, but this is what you have to do. All right, okay. Directions from the book, blah, blah, blah. You know, read them, follow them. They should be fine. What's the x-intercept, everybody? I'm not calling on the student. What's that x-intercept? -1 divided by 2, comma 0. And then what's the other one? 4, comma 0. And it is a mult 3. So the expected behavior of this, we had everyone stand up. It's a positive 2x to the 4th. Sorry, never was good at math there. And then the behavior is supposed to look like that. So you put it all together and get those multiplicities taken care of. Straight through, you could actually find a y-intercept if you thought about foiling that out. What's a -4 to the 3rd power? That's what I asked. What's -4 to the 3rd power? -64 times 1. All I'm doing is being lazy, and that ultimately is what would happen for the constants. So the y-intercept is what? 0, comma. I'm almost killing someone over here. It's taking all the oxygen in the room. -64. Did anyone say that?
Is it -64?
Anyway, let's move on. And then flatten. How do you flatten? You come close, and then you flatten. Don't put a little wrinkle in there like a little wave. All right? It just flattens. So what would an x to the 5th multiplicity do? What would like x minus 1 to the 5th power look like? The same, except probably a little bit flatter. What would an x minus 2 to the 4th power look like? Tangent, but it would be a bounce, but it would just be like the parabolic looking thing would be what? Wider, I guess. I don't know what else to say. All right, and then this is, what's the x-intercept? Wait a minute, what's the x-intercept? Is that an x-intercept? I get that all the time. 7, comma 0. Wrong! Okay, when you multiply this out, what would you end up with? 7x to the 6, and then it would just be, it would just look like that. Okay, and then the x-intercepts are 3, comma 0. I think you get it. It's over, right? -5, comma 0, right? Okay, but what would happen with this is you might have like a bouncer here like this. And then this might be, and that would be a lot higher than this. And I do want you to understand that when you're doing these sketches, they're just sketches. I don't care how high that goes when you're just doing a sketch. You would need your graphing calculator to actually assess that. All right? All right. Okay, now the last ones I'm just going to kind of shove at you. I may ask you to get your calculator out one more time, but not this one. Because when you actually type this in the calculator, you get most of the behavior that you need. So when you get into these questions, when they ask you to manipulate your viewing window, and we're not going to approximate the zeros. You're going to actually find them. It's not that hard to do that. But you might have to adjust your window. All right, this one's not so bad because you see all the things that you need to see. And so, get an appropriate window to try to see all the behavior. Okay, so let me pause this for a second. Poor about. And really poor about freaking out, saying the calculator's broke or whatever, and not knowing how to manipulate your window. Then I'll ask you, what'd you get for the X-Intercepts? We've covered how to find X-Intercepts quite a bit in here, so hopefully that is not an issue. So what I done did is I used negative 20 to 20, because look, I expect to see this behavior that I have right here, which you can't see because I kind of circled part of it. All right, so I expect to see an x to the third, and all I see is this. But you know what that is? That's this loop, and then this is going on forever here, and I'm probably missing this loop. So I'm missing an x-intercept that's off the screen. So therefore, I better extend my x's a little bit, and definitely extend my y's. And those are the windows that work the best. How many people found it without my help? Raise your hand. Okay, we need to get good with that and understand that. And then last one, I'm just going to shove this right at you. Zeros can be turned into, I just said the word on accident. Factors can be turned into zeros, which can be turned into, so you know what they give you at the end here? They say, for a cubic function, these are the zeros, x-intercepts. From them, find the polynomial. All that you have to do is FOIL. Just take a look at this number 55 real quick. Notice who I FOIL first because it's smart. If root 3 is a 0, then x minus root 3 is a factor. If negative root 3, then it's x minus a negative root 3. What you should do is FOIL the root factors. Because what happens to the roots? The middle term what? Cancels. And then you actually end up with something very easy to multiply out. So I don't think you really need my help on that. They should say with leading coefficient equal to 1 in these directions, because normally a higher level math class puts an arbitrary a out in front of this because it doesn't say anything about what is the leading coefficient. If it said with leading coefficient of 7, then guess what? A turns into what? 7, and you'd have to distribute it because it really is a 7 on the outside that you're multiplying the function by. But it does say, and it should just be treated as leading coefficient as 1.